Hello and welcome to our Media Milling Deep Dive webinar from Big Gardener. My name is John Kowalski. I'm part of the marketing team here. I'd like to welcome you. Today we have Mr. Andy Stumer. He is our Managing Director of VMA Getzmann, the manufacturer of the Dispermat. He'll be presenting. This presentation will last approximately 45-50 minutes. If we do have some time for questions, please log them in the chat box located in the bottom right-hand corner of your screen. Time consuming, we'll get to them. If we do run out of time, we'll follow up and get those questions answered individually after the fact. Also, we are recording this. So immediately following, you'll receive a automated marketing email with a link to this presentation. Feel free to take a look at it later, share it with colleagues, whatever you like. So with that, Andy, our dispersion guru here at Big Gardener, it's all yours, sir. Take it away.
Thank you. Excuse me. Thank you, John. Welcome, everybody, to our second part of the dispersion seminar. So today we're going to talk about the milling component, so media milling deep dive. Okay. We're going to just briefly do an introduction about the company, the relationship with VMA, where the company is located, and the design facilities. We're going to go right into the dispersion process, and then we're going to talk about the lab and production equipment capabilities we offer here, quality control capabilities, and then obviously our lab that we have in Wallingford, Connecticut for trials. We're going to cover that as well. And you can already see here on this picture that, you know, VMA is known to make high-end dispersion equipment. And this is just a snapshot, everything basically from a laboratory scale, pilot all the way up to manufacturing. And this is just an example. Obviously, there is different models and much larger machines that you can actually see here on this picture. Okay, so VMA is a German company, was founded in 1972. This beautiful couple on the top right, Hermann and Elke Getzmann, founded the company. And here at BIC, we have been the exclusive distributor for the VMA Getzmann product line since 1988. So going on almost 40 years, 35 years. The company is still owned by the family. So it's run by the two sons, Christian and Martin Getzmann. They have over 100 employees. And VMA is known to make high quality dissolvers, speed mills, basket mills, also horizontal mills for the lab space, pilot, as well as manufacturing arena. On the bottom right, you can see the very first Dispermat was introduced in 1973. Believe it or not, we still have customers today that are still running on with the original Dispermat that's 50 years old. We had one customer who about 5 years ago inquired about updating these models, and they ordered a new control panel, control box, and they're still running on the original motors. That's when we still had parts for these older units. But the motor technology is really good, and they will last you for a very, very long time. Okay, so this is just an aerial shot of the company in Germany. So they actually added on that building in the middle right here. They added a second floor to add on to their design capabilities and also manufacturing capabilities. So all the instruments and production machines actually built directly in Germany. The company is located about 30 miles east of Cologne in a very small town called Reichshof. VMA is known to also do a lot of custom work. So probably about 40% of everything that VMA manufactures is custom. We have a lot of new end-use markets. Fuel cell batteries come to mind with very specific application requirements, and VMA is able to meet them and produce equipment exclusively for that industry. So the facility is obviously in Germany, but here in the US, we are their distributor, and we have a laboratory where we actually show some of these instruments in Wallingford, Connecticut, at our sister company at Big USA. And we actually invite customers to come up there and take a look at the equipment and do trials up there. So we go right into the dispersion process. The big question is, why are we actually dispersing and why we're milling? So the bottom line is we want to have a better looking product, better performing product. It's about improving the wetting. We are really not trying to destroy any pigments or particles. All we want to do is break up these binding forces, almost like electromagnetic forces. They're called the Van der Waals forces, to separate these pigments or particles from each other, and then ideally reduce them back down to the primary particle size. That will in turn give us improved color strength, better gloss, overall better appearance. And then, of course, because we are breaking down particles, we're improving or increasing surface area, that will result in higher pigment efficiency or improved pigment efficiency. That will in turn help us reduce our raw material costs when we buy these materials for our formulations. In turn, we get a much better looking product. Formulation improvement is a consequence, and then obviously the net result will be a more consistent particle size distribution, smaller particles, and also better upscale results when we go from laboratory to pilot to manufacturing. So I'm having a lag here. Okay, I'm back. So if we don't do a proper job dispersing, we're going to have some issues, right? So number one, obviously, color shift, poor stability, pigments flocculate back together. We're going to see sagging, leveling, settling of our products. From an appearance standpoint, our gloss is going to be diminished. And then obviously we're going to have separation issues, which in turn can be solved by using the right additive, which our sister company, Big Additives, can supply. So here is a great slide. It kind of shows you, because we have customers sometimes, they want to stop the dispersing process after pre-dispersing with the dissolver blade. And here you can clearly see on the left, we have a pre-dispersed material that was just done with the dissolver disc, about half an hour of dispersing, between 18 to 25 meters per second tip speed. And then on the right is a fully milled material, same product, and you can already see visually the improvements to our formulation if we are actually do a good job milling. And today we're actually going to talk a lot about the milling part and what we want to watch out for, and the steps and how to have a properly milled material. Okay, so it's really important to remember that stability. So pigments require strong color fastness to reduce fading over time. So we get that done by properly milling our material, so our brightness will improve. That in turn will also give us the best looking color, ideally. Pigment size, obviously, the rule of thumb there is the smaller my particles, the better my color, transparency, and then again, formulation cost improvements, because I'm going to have to use less pigment in my formula because I'm creating more surface area, which in turn means dollars, and everybody wants to save money. So that's why it's so critical to have good milling technology that really helps you, produce small particles efficiently to help you save money. And then viscosity is also important. Usually if we have a good viscosity window, talk about 3,000 to 5,000 centipoise is ideal, because we can put in a good amount of energy helping us to really disperse these materials, and that will give us improved particle size distribution, help us with processing. If the viscosity is too low, we can still disperse or mill. It's just more difficult to put in the right amount of energy. And if the material is too thick, where it doesn't properly flow anymore, then it's very hard to put it through a basket mill or even a horizontal mill for that matter. So a good, viscosity window is very important when we are processing our materials. So important to remember here is we are really trying just to reduce our particle size. We're not destroying our particles or pigments. So just breaking up these van der Waals forces is what we're really trying to do, and take these agglomerates, turn them into aggregates, and then the aggregates, reduce them down to the primary particle size, which is the goal when we're actually milling our material. And it's really that the shear forces are responsible for that separation, nothing else. And then obviously the right additive package is critical to help us keep these primary particles then in a suspended state so they don't flocculate back together. And Big USA has a lot of different additives for different end uses, and they can really be a great resource if you have any questions or need formulation support. I like this slide. It just shows you different types of pigments and their different sizes. It's just a quick overview of the different pigments that we've been dispersing and what the technology is used for. So here on this slide, we kind of show you the dispersion process. So first, we have these larger clusters. We call them agglomerates. These are on the bottom circle there, you can see these larger building blocks, which are these clusters called the agglomerates. By using a dissolver with a Cowles blade, I'm able to turn these agglomerates into aggregates. But from the aggregate level, to get down to the primary particle level, I need to do the milling step, which is the vertical mill, horizontal bead mill, or the basket mill approach, what we'll talk about in a little bit here. So first, we are wetting of our solid particles, and then it's the mechanical breakdown of these agglomerates and aggregates into primary particle size. And then again, we want to stabilize the primary particles in our solution. So I really like this slide here. It kind of demonstrates, the different steps. So first, we start out with the dissolver disc or Cowles blade. We're wetting everything. When we reach about 10 to 30 microns of particle size, it's just a rough number, depending also on the formulation, is when we actually move to the milling step. And that's where we do our fine grinding and then bringing down these aggregates down to the primary particle size. And then you can see on the right-hand side on that picture, it kind of shows them in the suspended state with the right additives, that they will also remain suspended and don't flocculate back together. So that's the real goal in doing the dispersing process and what we want to do there. So on this slide here, it kind of shows you at what point you move from a dissolver over to a bead mill. So again, between 10 to 30 microns, this is just a rule of the thumb kind of number. But sometimes it depends on the formula. Maybe we need to go even smaller than 10 microns. We can work with a little bit over 30 microns, but that's ideal to move then over to a medium mill, allowing us to go into the lower micron or even sub-micron range. And for some applications, we have a nano kit allowing us to even go down into the super fine nano range. Here we have some examples of what we have done before, well below 50 nanometers of particle size for some high-end coatings or battery applications. Okay, so dispersing is always two steps. Remember, first, pre-dispersing, use a dissolver, Cowles blade. Critical to remember, the 18 to 25 meters per second tip speed is optimum. It's the right dispersion window. It will give us the best net result. Once we reach 10 to 30 microns, we then move over to our milling system, and then we can either use a vertical bead mill, a basket mill, or horizontal bead mills, and we have different options there depending on the formulation application, whether it needs to be scalable or not. So there's a lot of different roads that will lead us to Rome. Critical there, when we are milling, our tip speed is not as fast. We are milling with about 10 to 16 meters per second versus 18 to 25 when we are pre-dispersing. So that's just something you may want to write down. These are important numbers. Pre-dispersing briefly, container to blade ratio, about 1/3 the diameter of our blade to our vessel diameter is usually the rule of thumb. We can go a little bit larger if the viscosity is higher. If the viscosity is lower, we're going to reduce our blade size because we're going to be able to move the product pretty well in the container. As you can see on this table on the right-hand side, you can see different container sizes on the bottom, and then different blade diameters on the left. And you can see there is not one blade that fits all container sizes. So you have a sweet spot. For example, if I take a 1-liter container, I would say that probably a 50 millimeter blade would be kind of a sweet spot. And depending, if my viscosity is much higher, then I would increase the blade diameter all the way up to 70 millimeters. Or if the viscosity is very low, like water, I can go down to about 30 millimeters of dispersion blade diameter. So these are just some examples. We have those tables also for larger volumes online. If you want to check that out, they can be very helpful, helping you dial in exactly the right blade for your application. Okay, peripheral speed, we already talked about that a little bit. Pre-dispersing 18 to 25 meters per second, milling 10 to 16. Rotor speed, the formula is exactly the same. So we actually are calculating here the RPMs times pi times the diameter of our milling disc. If we want to express meters per second, we divide everything by 60. But keep in mind that then you have to also express the blade diameter in meters. So if you have a 50 millimeter blade, that would be 0.05. So let's say I run 3,000 RPMs. So I have 3,000 RPMs times 3.14 times 0.05. And then you divide everything by 60. That would give you the tip speed in meters per second for a 50 millimeter blade at 3,000 RPM. And you would do the same calculation for when you're milling with the rotor. You just measure the diameter of your rotor and then use the same RPM value what you dial in on your mill, as well as the pi stays the same, 3.14, and then you divide everything by 60, and then we'll give you the peripheral speed of your rotor in your basket mill or your horizontal medium mill. Again, important to remember when we are milling, 10 to 16 meters per second is the optimum tip speed or rotor speed. Then we have something we covered last time more extensively. It's the donut effect. When we pre-disperse, really important, if I have the optimum viscosity, I'm putting in the right amount of energy, I should see the appearance of a donut being formed in my container. That's the visual cue that tells me, hey, look, I'm putting good amount of energy in there. I'm pre-dispersing. The process looks all right, as long as I have obviously the 18 to 25 meters per second, and I have viscosity in the optimum range, 2 to 5,000 centipoise. I should then see the appearance of a donut being formed in my container. So just to summarize from the last presentation, for the pre-dispersion part, to optimize that process, duration of the pre-dispersion or dispersion, about 15 to 30 minutes. We want to see ideally a donut effect. Tip speed again, 18 to 25 meters per second. The blade to container ratio, about 1/3 diameter, is optimum, but we have variability there depending on the viscosity. Also, the right type of impeller disc or cowl split. There are a lot of different options online, a lot of customizations. So whatever works for your process, make sure that you choose the right impeller disc. We can also guide you or help you guide you. When we learn more about what you're trying to do and about your formulation to recommend the right type of impeller disc. The amount of mill base is important, so we recommend about a 50% fill ratio in our containers. We can go as high as 70% and as low as 40%. You don't want to go over 70%. Obviously, when you put in the energy and the speed, you're going to create that donut and vortex, so you may spill your mill base over the container edge. So try to stay below 70%, and if you go below 40%, then it's more challenging to actually oscillate and put the dispersion blade at the right height in the container because you don't have a lot of mill base to work with. So about 50% is ideal. Pigment filler concentration, okay, that's formulation dependent. When we are pre-dispersing, temperature is not as critical, but we still like to be on the lower end. We are not putting in a tremendous amount of energy just using a cow's blade. We don't have any media there. So the amount of energy we're putting in is somewhat limited compared to the milling step. But we still want to make sure that the temperature stays on the lower end, depending also what you're trying to do, if you're running solvents or waterborne products. And then ideally you want to have a jacketed vessel for cooling capability that will help you maintain that temperature. And then again, the additives, I always bring them up, but they are so critical. We see it all the time. Ineffective additives will give you poor results. And when we have customers come into our lab in Wallingford, we have the ability to play around with different additive packages. And customers are always amazed how much improvement they see with their respective formulations, but changing one additive out for another, especially dispersant agents or defoamers or anything like that can really help improve your product. And then when we reach the right particle size, again, between 10 to 30 microns is when it's time to start the milling process. And that's what we talk about today. So dissolver, and only a limited amount of energy input due to the fact that we only use a blade, no media. Limited shear force is the result. We are only deagglomerating. We are not breaking down to the primary particle size. So it's just taking these agglomerates and turn them into aggregates. However, it's an important step for any dispersion process. So don't think you can just mix something up and then throw it into a mill. You probably, if the particles are too big, you're going to end up with a clogged mill, clogged screen, or a stuck dynamic gap. So depending on the mill design, always make sure that you properly pre-disperse and then start the milling process. And of course, we already talked about that. The product appearance and color is going to be poor if you only use a dissolver. So by milling the material, we can put in a lot more energy. We have the beads with the rotor. That really helps us break down these particles or these binding forces, break up these van der Waals forces, and turn these larger particles down to the primary particle size. That will give us the best looking product, smallest particle size, obviously helps us again saving money because we create a lot more surface area, meaning that we don't have to put those expensive raw materials in our formula when they're too large in particle size, wasting money and having poor results. So what happens actually in a bead mill is very simple. So we have our chamber, and inside of our chamber, we have a rotor, and then we fill that chamber with a certain amount of beads, depending on the size of our milling chamber or the mill size. So once we have the beads inside of our milling chamber, it's time to add the product, and then we turn up the mill. And then we run it again, 10 to 16 meters of tip speed is optimum. We should see good flow through the mill and have good processing performance. So what happens then inside is that these beads will collide at very, very fast rates, right? So they drift towards each other. And by doing so, they will create the shear and push away the pigment particle or the aggregate. And that shearing motion is actually what's causing the aggregate particles to separate, or the binding forces to separate, and turn these aggregates down to smaller particles and smaller until we reach our primary particle size. So it's not really that we are crushing the pigment or destroying them. That's not the goal. We're really just trying to break up these binding forces and turn these larger aggregates down to primary particle size by simply breaking up these binding forces. So that's what happens inside of a mill. And then again, wetting, stabilization, and we should end up with the primary particle size if we mill long enough. That's the whole goal here inside of a mill. So important here, when we are milling, obviously, the mill design is one aspect, but we also want to look at the media. So ideally, you want to use media that's as heavy as possible, but don't use steel, because that will also cause other issues during the milling process, such as discoloration, right? Milling is an abrasive process. If I use steel media or metal media, that will then bleed into my slurry. So if I'm trying to mill a white material, the net result will be a gray slurry when I'm done, because all the media, the metal particles will actually bleed into my slurry because of the impact of the media with the milling chamber, and as well as the media impacting each other. So ideally, we recommend that you use a zirconium oxide. They are much better than glass beads. Glass beads are not ideal because you can already see the specific weight. Specific weight on a serum stabilized zirconium oxide bead is about 6.1 versus 2.5 on glass. So about 2.5 times heavier. So that will give us much more higher kinetic energy, giving us better milling results. So stay away from glass. The other issue that glass has, it can shard and break up during milling. And then what happens is you end up with these tiny glass particles inside of your slurry. You have to filter them out. And then you also will have very uneven bead wear. And that will give you inconsistent milling results. So by using a very durable, high quality zirconium oxide bead, I don't have any sharding problems. And also the bead wear will be kept to a minimum. And I will not have any bleed in of any type of metal contamination into my slurry. So for most formulations where ceramic, where it wouldn't impact the slurry performance, zirconium oxide is probably the best the market has to offer today. But definitely for most applications, much better than glass, and obviously because of the discoloration issue, way more preferred over steel or metal beads. Okay, so there is obviously different types bead sizes depending on the starting particle size and how fine I want to mill. So we can actually go, even we have now beads that go down to 0.1 and smaller. It's not on millimeters, it's not on the screen, but they're used for nano milling and super fine particle size requirements, less than 50 nanometers. That's something like that. You would use beads that small. Our equipment has the capability, and we are able to accommodate those small bead sizes. So here shows you kind of visually the influence of our bead weight. For example, if I look at this board with that nail, if I have a small hammer like a glass bead, right? It's very light. It would take me maybe many impacts, 100 impacts to drive that nail into the board. As I'm increasing the size or the weight of my hammer, then I'm reducing the number of impacts it takes to drive that nail into the board. So that's kind of the same principle we see with milling beads. So the heavier the beads, the higher the kinetic energy, the better will be my milling performance. So kind of shows you in a different way, but I kind of like the display here. And that's a formula just for the key factor for milling, about that kinetic energy. So it's the weight of our beads times the velocity of our rotor speed squared divided by 2. That will be the calculation of the kinetic energy, what we actually would experience inside of our mill. So that could be an important formula if you want to calculate. If you talk to somebody, a bead supplier, and you want to figure out, hey, what would be the kinetic energy using one bead versus another bead type. So that can be very helpful formula to use to calculate that. Okay, so on this slide here, uh, kind of shows you the same thing as on that first bead slide, but here you kind of see it more broken out. So you see the larger balls here, these are the beads. And then we have the particle or the aggregates in that smaller circle, kind of in the middle. And that's actually where that shearing takes place. So by colliding these beads, or by the collision of the beads, right in the corner where they meet is where the shear forces are being created. And that will actually push that particle away. And because of the shear, will break up these binding forces and turn these aggregates down into smaller particles. It's kind of like I like to see it that way. If you remember when you were a little kid and you were sitting in a bathtub and your mom gave you a rubber duck and you were trying to catch the rubber duck with your hands, right? What happened? The rubber duck would always get away from you. You would never or hardly ever get it between your hands, right? So that's kind of exactly what's happening inside of a mill. By the beads colliding together, we are pushing away the pigment particle, and that's actually what's causing that shearing and breaking up of the particle. It's kind of the same principle, and the probability of actually having a particle right in between two beads and getting destroyed exists, but it's very small. Uh, it's almost non-existent. So destruction is not really the goal, anyways. But the probability is very small that you're actually destroying the pigment. So it actually is really just the breaking up of these binding forces. Okay, so here are some critical bead milling parameters. So particle size after pre-dispersion with the cowl's blade, when pellet blade, 10 to 30 microns. Bead size and weight are important. The bead type, zirconium oxide preferred, don't use glass or steel. For the reasons we talked about, the amount of beads are determined by the size of your milling chamber and the mill design. The shape of the beads, obviously, we want to keep them perfectly spherical or buy them perfectly spherical. We have seen some bead suppliers, they send out a perfectly good sample. When you look at that under the microscope, they're really perfectly spherical. And then you buy the first lot, and then all of a sudden it look more like footballs and are no longer perfectly spherical. So you really want to get a good quality bead from a good, reputable supplier, that they're really always perfectly spherical. Otherwise, you'll have uneven bead wear, inconsistent milling results, and you will not be happy. Tape speed, again, pre-dispersing 10 to 16, milling 10 to 16 meters per second. Product temperature, when we are milling, we are putting in a lot of energy into our mill base. So cooling will be critical. You must have a good chiller or cooling system in your facility, allowing you to really keep the temperature as low as possible. If you don't have any cooling, you'll the temperature will rise up very rapidly to dangerous levels, especially if you're running solvent materials. Excess of 100 C is not unusual. So you really need to look at the flash point of your solvent and make sure that you have a chiller capable of maintaining a low temperature. Energy input, so how much energy are we transferring into our mill base? That's dependent on the speed of my rotor and, of course, the weight of my beads. And then how often does my mill base circle through the milling chamber? We call that number of passes, the overall milling time, and then viscosity again of the mill base is important. You want to have it in an optimum window so you are able to put in just the right amount of energy. If the material is too thick, yeah, you can put energy, but it won't flow properly. So you can't get it out of the mill or put it back or get it back into the mill. So the material needs to flow. Milling tool diameter. So depending if I'm using a horizontal mill or a basket mill, obviously that plays a role. Of course, in my calculation of tip speed, that's really important. And then finally, the type of material that we are using for our rotor or even milling chamber. We offer stainless steel as a standard option on our horizontal mills. But there are different materials like ceramic, zirconium oxide, there's hard steel. So there's a number of different materials available depending on the requirements or what's compatible with your formulation. And then, of course, the type of mill. Are we looking at a horizontal bead mill? Are we looking at a vertical mill, like a basket mill? So that's also something that needs to be looked at. Are you trying to do a batch process? Then maybe a basket mill will be sufficient. Are you trying to do, go through or pass through? Then maybe a horizontal media mill might be the better option. But it really also depends on the final particle size. So with the basket mill, I'm easily able to go down to about 500 nanometers. If I want to go much smaller than that, then I may have to use a horizontal media mill. Again, that is formulation dependent. So here is a great picture just explaining our philosophy behind our Dispermat design. So in the middle, you can see a standard Dispermat. It ships as a dissolver with a cow's blade or impeller blade. And then you can add on different attachments depending on your need or your application. So on the top left, we can add a rotor stator for homogenizing or emulsifying. We can add a vacuum system on the top right. It's called a CDS. Some people like to disperse under vacuum to remove any type of air. We can also mill under vacuum. That will improve the milling efficiency. Think about air bubbles are tiny little air matrices, and they can buffer the blow of the beads, and that kind of minimizes our milling performance or efficiency. So by removing air, I can speed up the process and have a better milling process, or milling cycle. On the bottom left, we show you the APS, which is a vertical bead mill, or some people call it a pot mill, which is perfect for the lab for very small volumes. Not really scalable because you can add 100% bead loading. So if I'm using, let's say, 1 liter container, APS 1000, I can have 500 milliliters of slurry, and I can add 500 milliliters of beads. So I have a lot of beads going in there, which give me excellent milling performance. But let's say I want to scale that up to a ton. That means I need 500 kilo of beads, well, depending on the volume, right? If I have a 1 ton container, I put 500 kilo beads to 500 kilo slurry. That question becomes, how do I handle that? So maybe really great for lab and small pilot, but not really suitable for manufacturing scale. For that, we have the TML basket mill, which is on the bottom right, which is perfectly scalable. I can use a TML for very small volumes down to a quarter liter, a quarter quart, all the way up to 2,000 liters of material. I'm able to efficiently mill, and I would get very, very good upscale results from lab to pilot manufacturing. We also offer the ASC, sorry, that's a wall scraper unit for very thick materials, not really for milling, but if you are dispersing something like a paste and you want to scrape the container wall, we offer that ASC that will keep the container wall all clean and make sure all the product gets pushed in the middle of our container, when then the dispersing blade will take over and disperse our material. Okay, so here's just an example of the kind of our flagship, the AE dissolver. Here we have a quick change system that you can see the clamping ring right below the motor. Shows it nicely. That's what we actually open up. We open the clamping ring, we turn this assembly 180 degrees, and we can pull it out, and then we just pop in a basket mill. So the same machine will function as well as a dissolver, also as a milling system. Depending on the size of the machine, we can go up to 20,000 RPM, which is very, very fast. But if we have a small diameter blade or milling disc, it's needed to reach the optimum tip speed. We also offer, for certain applications, they require explosion-proof models. We We have those in our portfolio as well, not only for lab scale, but also for production. And then we have software, WinDisp, that is available for our premium models that will help you also with upscaling all the data, storing it, and then maybe even creating a nice looking lab report. So the Dispermat shines because of the modularity approach. Mr. Getzmann was the first one that really thought about offering one piece of equipment for many different applications, helping a customer save money, but more importantly, desk space or bench space, because you don't need so many different machines for one project or different projects. Everything should be done on one machine. So a Dispermat will function as a homogenizer, emulsifier, or disperser/media mill, which makes it really a standout product. I want to talk briefly before we go into the basket mill about the motor technology that the Dispermat uses. So it's all direct drive. So we don't have any belts or any wear parts really in the motor. So the shaft will go directly into the motor. The result there is that the motors are extremely quiet, so you can hardly hear them. We have customers, we had them at the American Coating Show, at the Battery Show in Detroit. We had one up at 20,000 RPM, and the customer couldn't believe it because they thought the machine wasn't even running. So they're extremely quiet, have very low vibrations, and they will, again, last for a very, very long time. We have customers that running Dispermats that are over 40 years old, still on the same motor technology. I've been with Big for 18 years, and I have never seen one broken motor. I've seen broken busted control panels, parts wear out, that's all normal. It's milling is wearing down equipment. However, I've never seen a worn out or burnt out motor. So that just speaks for the quality and performance of the technology. Okay, so the basket mill is the attachment that goes onto our Dispermat. It's a vertical bead mill design. So basically, it's for processing batch lots. I have a certain amount of product in a container, and I want to mill that. And I'm not adding more material to it, doing the milling process. I'm just strictly using or milling a certain quantity inside of my container. So it's a batch process. So with the basket mill, as you can see the picture on the bottom, we have our milling chamber. The milling chamber is double walled for cooling. You can see there are actually cooling channels that go through the basket all around it. That will ensure that we can keep the mill base at optimum temperature and that don't overheat it. In the middle, we have our milling disc. And then right above the milling disc, you can see that those little fins, that's actually our vortex blade or steering system. What that does, it actually helps us create a vortex and then suck the mill base into our basket. Where then, obviously, you don't see that on this picture, but there are beads in here. That basket will be filled with the zirconium oxide beads, and that will then take care of the milling process. On the bottom of our milling disc, I have a screen. Depending on the size media, I can change the screen mesh size. So standard is 0.5 millimeters. So I can use 1 millimeter beads, which is good for most applications. And then right below the screen is used to separate the mill base from the beads, so the beads will stay in the mill or basket. And then below the screen, I have a cow's blade. So that cow's blade is not there to disperse the material. It's already dispersed. But what it does, it helps draw the mill base out of our basket and then pump it back around to the top, where then that vortex with the fins will take over and suck it back in. So I have very good circulation of our mill base in and out of the basket, giving me optimum milling performance. The huge advantage there is there are only very few parts inside of this mill that are actually wearing out. So I have my vortex wheel and I have my milling disc and a little bit my screen, but I don't have any O-rings, no seals, nothing like that, what you would see in a horizontal mill. So from an efficiency standpoint or maintenance standpoint, this is a lot more attractive to a user because I can clean this on a lab scale in maybe 10 minutes, or manufacturing, maybe I need 30 minutes. When a horizontal mill, it would take me an hour, maybe 2 hours to disassemble and then replace or clean all these parts. There's also there are a lot more wear parts in a horizontal mill than I have here in my basket mill. So this is a very attractive option to milling small volumes, quantities, lab samples, as well as manufacturing size samples very efficiently and very easily. And also the cleaning is much easier compared to a horizontal media mill. So there are a lot of customers that are actually moving from it. We get calls all the time. The customer called the other day and he's like, I have a 3-roll mill. Could I use a basket mill? Absolutely. We had an example of a customer. He came to the lab with 3 different colors. It was an ink application, and they were using a 3-roll mill. The yellow, it took them 14 hours in one go to mill the yellow to the right particle size. So they booked 3 days in the lab to do a demo or a trial on the basket mill. We were done in 1 hour and 15 minutes. We reached the same particle size with the basket mill, what took them 14 hours on that yellow. And it wasn't any different on the purple and green that we did. So one took an hour and 40 minutes, and the other one was done also in an hour and 15 minutes. Needless to say, the customer went back to their lab, did all the post-trial analysis, analytics, and within 2 weeks, we got a purchase order. And they're still happy running the basket mill. They're also a lot safer and easier to clean than that 3-roll mill. Okay, so on this slide actually kind of shows you on the picture what happens in the basket mill. So on the bottom here, on the left, sorry, you can see the beads in the basket and then kind of like the fluid motion. So the screen on the bottom actually draws out the mill base through the screen and then pushes it to the top, where then that vortex will sucks it back in. So we have very, very good circulation of our mill base in and out of the basket. So then we just remove it. And the way we start the cleaning process is actually very easy. As soon as we lift up the basket, just right above the mill base, just a little bit above, so the cow's blade doesn't touch the mill base, we run it for a couple minutes and then let all the material kind of flow out. That way we kind of got most of the excess material is removed from the mill. Then we're going to take that container and replace it with a container with solvent or cleaning agent or water if you're running a waterborne material, and then submerge the mill and then run it for a few minutes, rinse and repeat until there is no discoloration anymore. And that's the hardest part of cleaning that mill, really. So if we want to be really thorough, we actually open up the screws on the bottom. There's 3 screws or 4, depending on the mill size. We remove the screen, catch the beads, and then put them into an ultrasonic bath for kind of a final cleanup. And then we can reuse those beads and onto our next batch. And that doesn't take long at all compared to like a horizontal mill. So here is a larger basket mill for a small production unit. So there you can see it. The screw right there is actually where we feed in our beads with the funnel. You can see the cow's blade on the bottom, and then the product entry on top in the middle right there by the stand. The cooling lines go through these bars that are holding the basket. So I want to say a couple of things about the basket design. There are some competitors out there. They make really good products, but their mill design is different from ours. So they actually have basket mills that are open on the side, where they have a screen. We have a screen on the bottom. They have a screen on the side. We don't have that. The reason is we believe that cooling is really important. And that's the area where you have most of your energy build up or heat build up. So this is where we actually cooling the mill base right behind these walls. So if we have a screen right there, we can't do proper job cooling. But most importantly, the beads are going to impact that particular area all the time. And by having a screen right there, we're going to see heavy wear on our screen. And that means a lot of screen replacements. By having that closed up, we're not going to wear down our screen and we're going to have improved cooling. So that's the reason why our design, all that is closed up to give you optimum cooling performance and also minimum wear on the screen. And our screen is on the bottom, so that cow's blade takes care of drawing the mill base back out and around. Just an example. So we can go up to about 2,000 liters of material with this batch system, as low as 0.25 liters, quarter quart in the lab. Upscaling is very easy. We can almost scale up one-to-one from lab to production. Also, that's formulation dependent, so this is not an exact number, but we are pretty close. Cleanup, again, very easy. The pumping wheel does a great job drawing the mill base into the basket. Very simple design. Again, the handling is really easy compared to a horizontal mill or even a 3-roll mill. And then with a nano kit, we have the ability to go down to 0.2 millimeters of bead size on our basket mill. So able to produce very, very small primary particles. Here is an example of a production scale system. We have a customer in St. Louis that bought 2 of them. And what's great about that system, it's the TM1000 for production. Here you have a 2-in-1 system fully integrated. So on the picture, you see that gentleman standing there with the gray sweatshirt right behind in the blue drum. You can see the cow's blade is actually not installed. It's leaning against the blue drum. So the cow's blade will go on the dissolver shaft, but right above the dissolver shaft, we already have our basket, so we don't need to change anything. So in this scenario, we put the container under the mill. We first pre-disperse. When you reach the right particle size to start the milling process, we initiate the milling step by just pushing a button on the control panel. The basket will then lower, and now we are milling without having to move containers around to different systems. So everything can be done on one machine in one location without having to move around any containers. So that's a huge advancement in dissolver/milling technology for production. Saves customers a lot of money because they buy one machine instead of 2. They use only half the space that they would normally need. So their customers purchase 2 machines. They are workhorses. They run 24/7, and they absolutely love them. These are really, really good machines for manufacturing pigments or battery products or anything you want. We can even make them under vacuum. Here you have the APS vertical bead mill. Again, I already talked about that before. We called it the pot mill. This is more for laboratory scale. Again, not really scalable for production due to the volume of beads it would require to run that in a production setting, but really good, very easy to use in a laboratory setting. APS stands for air pressure system. So we basically have our mill base inside of our container. If it's a 1-liter container, 500 milliliters of mill base, 500 milliliters of beads. When I'm done milling, I just have my cover that's already closed. I hook up an air hose, there's an air socket, and then I pressurize my APS system after I remove that drain plug. And then I can automatically purge my mill base, into that container right below. It's a really effective way of milling and removing my product. When I'm done and all my product has been removed, there's actually a screen that's not shown on this picture that separates the beads and keeps them back in the container. I put my drain plug back in place, fill up my container with cleaning agent, and then run it for a few minutes and then purge it out until all my beads and my container is pretty clean. So a very easy way of running a milling process, as well as cleaning. And we can go up to 7 liters standard, but we have made pilot systems for up to 60 liters. So that's possible. But remember, bead handling becomes more problematic the larger I go with my container size. Okay, just a close-up here. APS system on the left, you can see it closed with the media. And then on the right here, we have the air hose hooked up. And then we are draining our material, our mill base, into a container right below. Beautiful little milling system. We also have horizontal bead mills. We call them the SL for the laboratory scale. We have that in Wallingford, Connecticut. And we also have production scale for the RS. So we cover that milling aspect as well. On the SL, obviously, it's a horizontal mill design. You can either set it up pass or recirculation method, depending on your formulation or the particle size requirement. It has already an integrated pumping and steering system that forces the material into the milling chamber. RPM can go up to 6,000 RPM. We are able to independently regulate the rotor and pump speed, which is really nice, and also offering different types of materials, ceramic, hard metal, or anything, even polyurethane for the rotor is an option. And then we have also different coatings that we could offer, DLC, diamond lead carbon coating for milling chambers and so on. Some customers don't want any type of metal contamination. And then again, we can use for the standard mill 0.3 millimeter media up to 3 millimeter, and then with the nano kit, which allows us to use them very small media 0.1 to 0.3 millimeter if needed. And then we can take a standard SL and actually convert it over to a nano mill by just buying a few parts that will then help us do that. Quality control, just some critical components here I want to mention. So with our C technology, which is kind of a control panel, allowing you to really lock in all the different parameters, store data by product name, and then later on, when you want to run the same batch or same product again, all the critical values will be remembered, and then you can put in the same amount of energy, speed, and also important, the cutoff values. Let's say you have a temperature threshold and you don't want to exceed, in this case, you can see 45C. It will automatically stop the machine once it reaches 45C or run with a different speed or different energy input. So you can program that. On the bottom, you see 45C. On the top, the cutoff value is 80C right there. So depending on what picture you look at, but it's up to you how you want to set that up. And then we can do what's called a net power calibration with the C technology, which is nice, especially some customers don't want any interference of the machine power when they look at torque value or net energy used to disperse X amount of material. So by doing a net power calibration, I'm actually running the Dispermat or the mill without any product for about 30 seconds. And then the machine will automatically factor out the amount of energy it took to move the rotor or move the dissolver shaft without product. So then all the values that I'm seeing in terms of torque or energy are strictly related to the product and not the machine input. Then we have the beautiful lab in Germany at VMA. So if you have a sister company over there, or you happen to visit Germany and would like to see the lab or come in for a trial, more than welcome. We have also a beautiful lab in Connecticut. This is an older picture. We have a lot of new instruments in there, as you can see right here, the AE6 as well as an SL mill. And then next year in January, we're going to have a VL vacuum system for vacuum dispersing, great for batteries, fuel cell, or even certain specialty coatings. And we also have the new CV3 Evo, which is our brand new model for lab scale. Beautiful little machine. If you're interested in learning more about it, we can talk to you and show you some things online or come to the lab. So the lab in Wallingford is a really fantastic facility, not only to show customers our milling and dispersing capabilities, but also bringing in our colleagues from the additive side, really helping customers with improving formulations, looking at different additive packages, and how do they work with our dispersing equipment. So we are not just a company that sells you a piece of hardware and then you're on your own. We are really a full turnkey solution provider, providing everything from the correct hardware setup, scalable from lab to manufacturing, with the right additive and formulation support if you require that. So that's the beauty of working with BIC, is that we are able to leverage those synergies between our companies. And if you're not interested in running a trial, you're still welcome to check out the equipment and take a closer look at what we have to offer. So with that, I think we have just hit the 3 o'clock mark.
Yeah.
You guys today. Thank you.
Great stuff, Andy. Thank you for the expertise, and folks, take a look at when we close this out in a moment. Take a look for that recording. Lots of great information in here, and I know Andy covered a whole lot of ground really fast. So take a look at the recordings, take screenshots, look at it, at a slower pace. If you do have questions, hit reply to that automated message. Reach out to us. We'll get you in touch with Andy or someone on his team to get you taken care of. So we appreciate your time. Thanks for joining us, and we look forward to seeing you on future webinars by BIC Gardner. Have a great rest of your Tuesday. Thank you.